The purpose of this video is to illustrate Weitzman discounting using a simple numerical example. I'm representing uncertainty about the discount rate using a very simple three-level discrete probability distribution. So in this case I've got only three levels, the lowest rate being 0, 4% and 8%, and the probabilities of those different levels are 0.25, 0.5 and 0.25. So that information together constitutes a probability distribution, and the expected discount rate is 4%. I'm assuming that this uncertainty about the discount rate does not start immediately. In fact, I'm assuming that for this purpose of this illustration, that for 25 years we know what the discount rate will be, and it will be 4%. For the next 25 years, our uncertainty will increase up to the level that I've just defined, 0, 4% or 8%, and then after that, the uncertainty will stay the same over time. This is clearly highly stylized and very simplistic, but it's sufficient to illustrate what's going on when you do Weitzman discounting. I'm going to show you how I've entered in the numbers over a 100-year period. So in this first column I've got the year from 0 down to 100 years, and in the second, third and fourth columns I've got those three different discount rate patterns that I illustrated in that graph. So if I track down, you can see that after year 25 the low rate starts to fall and the high rate starts to rise, and that continues until we get to year 50, and then it reaches 0 and stays there in the low rate, and it reaches 8% and stays there in the high rate. So these numbers here are actually the numbers that I've used to generate the graph. Now the next thing is to convert these discount rates into discount factors, because it's discount factors that are the important thing to understand what's going on with the Weitzman discounting. So what I've got here is these three columns, and they show the discount factor under scenario 1, scenario 2 and scenario 3. All three of those are identical until you get down to year 25, when the discount rates start to diverge, and then because the discount rate is less in this first scenario, the discount factor is more than it was in the for the mean discount rate, and it's less again under scenario 3 where the discount rate is higher. And that pattern continues on until you get to year 50, and then you can see that under the 0 discount rate, which applies from then on in the low discount factor scenario, then there's no further change in the discount factor, while in the high discount factor scenario it does continue to change. And you can see how the discount factors evolve over time for the three different scenarios in this graph. So the low discount rate means that the discount factor stays high, whereas the high discount rate scenario, the discount factor continues to fall. Okay, so clearly we've got these three different scenarios, and because of the way that I've represented the uncertainty as not really starting until after year 25, then they only start to diverge after that time. The next thing that I've done here is calculated the expected discount factor, and this is the critical thing in Weitzman discounting. Let's look down here at say year 50. So the expected discount factor is the weighted sum of the three scenarios. It's that value times the probability of scenario 1, which is back here, 0.25, plus that value times the probability of scenario 2, which was 0.5, plus that value times 0.25 again. And so the weighted average or expected value of the discount factor is 0.15. And that gives a certainty equivalent discount rate of about 3% for year 50. So that's saying that in year 50, once we take the weighted average of these different discount factors, if we had just used a discount rate of 3% and assumed that that was known with certainty, then we would have got the same discount factor as that expected discount factor for year 50. And as time passes, this this certainty equivalent discount rate is falling over time. So that's the point that I'm making, that doing it this way, calculating an expected discount factor, is the equivalent of a declining certainty equivalent discount rate. See, it's started off at 4% and it's now down to about 1% by the time you get to year 85. Okay, and the result of that graphically, so here's the expected discount factor, and if we compare that to the discount factor we would have got if we had just used the mean discount rate and treated it as a deterministic discount rate, here's the comparison there. You can see that the deterministic discount factor of 4%, this sort of dark red line, ends up having a lower discount factor than the one that accounts for the fact that the discount rate is uncertain. And the reason that this happens, you can sort of get a sense of it from this figure, that when you vary the discount rate up and down either side of the mean, like this is the mean one here, the reddish one, making the discount rate higher lowers the discount factor, but not by all that much. In fact, because there's not a lot of room to move. But making the discount rate lower raises the discount factor by quite a bit. So it's not a symmetrical thing. An increase in the discount rate has a small effect on the discount factor, whereas a decrease in the discount rate has a relatively large effect on the discount factor in a positive way, in the upwards direction. And so that's why when you take the expected value, you end up with a higher expected discount factor than you get from just using the mean as a deterministic value. So that's basically the point of Weitzman discounting. However, I would point out that if you allow for sort of a realistic time frame for uncertainty about the discount rate to kick in, I've argued that you can probably make a realistic guess at the discount rate for at least 20-25 years, and so the uncertainty starts to increase after that, and it doesn't become really large until maybe 50 years in the future. So if you agree with that, you may or may not agree with that, but if you agree with that sort of stylized sort of summary of how it might go, then the effect of the Weitzman discount approach are not all that large, because you've done most of the discounting by the time you get to about year 50, and so the difference that it can make from then on isn't all that large. Now that depends on my assumption that I've used here, that the mean discount rate that we start with is 4%, and that we'll stick with that, but that the uncertainty will increase over time. So that's a very specific assumption. But nevertheless, I'd say that in general, it will be true that the Weitzman approach won't make a large difference in the early years, in the early, at least the early few decades of discounting. It will only become an important factor later on. But by that time, most of the discounting has already been done. So it means that for a benefit that occurs in about year 100, instead of having a discount, instead of counting at about what does that look like? Maybe 2%, it might count at about 7%. So the discount factor goes from maybe 2% to 7%. I'm guessing what that is. We can check what it is actually by going to the table. So in year 100, okay, it is about 2%, so 1.8%. Sorry, that's not the one I'm looking at. There it is. Yes, 2%. That's 1.9, it's almost exactly 2%, 1.98% is the discount factor if we use the mean discount rate of 4% in year 100. Whereas if we use the expected discount factor, it's actually about 7%. So it's increased the weight that we give to a benefit in year 100 by a factor of 3.5, roughly. So that sounds like it's made a big difference. But it hasn't made all that big a difference because the starting discount factor is so small. So it's still only 7%. 7% is 3.5 times bigger than 2%, but it's still not very big. So a number would still be substantially discounted, just not by as much as it would have been if we'd stuck with a deterministic discount rate and used 4% the whole way.